Let's get into the specifics of the regression equation. The regression equation represents the line that approximates the values in a scatter plot the best. So in this picture, we have a scatter plot relating X data values, which represent a student's high school GPA, and Y data values, which represent their university GPA. So we can see this guy right here had a low high school GPA, but a very high university GPA. And, maybe this person right here, their GPA in high school, you can see was just above a 3, and in college, it's the same. So their university and high school GPA didn't really change very much. If we got these data points as a sample and we calculated the regression equation, so the equation of this red line that's trying to fit the data the best it can, it might go through some of the data points, it might not. The equation of this line would take on the form y hat equals a plus bx. It's a little bit different looking than what we're used to with linear equations, mx plus b, but just realize that all that we've done here is put the mx term second, and then we start with the y-intercept value. And the letters A and B here don't necessarily have any meaning. They are just letters picked in a textbook. You might see this equation written as y hat equals b naught plus b1x. Again, we're still saying that this guy attached to the x is the slope, and the value that's by itself is the y-intercept. In this scatter plot, we can see that the y-intercept of the regression equation is here. So it's just below 2.5. So the y-intercept might be the point 0, 2.4. The slope of this line would be whatever b is, and we would have to use other points we would have to use all of these points in the scatter plot to calculate that slope. We'll get to that eventually. Remember that the regression line goes through the point of averages. So if I took all of these x values and I found the sample mean of the x values, that would be x bar. And so that point might be right here, and we would go through that point, and we would do the same thing for the y values. So the sample mean of the y values would be y bar, and the regression line always goes through the point of averages. So let's talk about how you use all of that data, all of those points in our scatter plot, all of those x, y values, to create the regression equation. So starting with A, the y-intercept. The formula for finding A is y minus b times x bar. So A is dependent on the point of averages, x bar and y bar, and the slope b. So in order to find A, we actually need to find b. Calculating b by hand can be quite tricky, especially if you have a lot of data values. The formula for b is to take each data x value, subtract the average x value, multiply that difference by each data y value minus the average of the y values. And so you multiply each of those x and y combos together for all of these data values, and then you add them, you sum them up. Once you have that sum, you divide by the sum of, again, all of the difference of each x with the x average squared. That's how you calculate b. So it takes a lot of time. So hopefully you're not surprised to hear that we'll definitely be using technology to evaluate this number. There is another formula. It's a little bit simpler, and it is r times s sub y over s sub x, where s sub y is the standard deviation of the y's and s sub x is the standard deviation of the x's. The other thing, though, that you see in this formula is r. R is a new letter. R is called the correlation coefficient. And again, unfortunately, calculating the correlation coefficient is not that simple. So maybe this formula really isn't that easy. But technology, it's going to do it for us. Let's do an example with some data. So suppose I take a random sample of mothers and daughters, and I see how tall each mother is and how tall their adult daughter is. So one set of mother and daughters, the mom was 61 inches tall and the daughter was 64 inches tall. And then we have 65 inches tall and 65 inches, 62 for the mom, 63 for the daughter, etc. And so I went ahead and plotted those on a graph here. And I used Desmos to do it, but you could do it by hand. So each one of those dots represents a mother and daughter pair. I want to try and draw the line of best fit or calculate the line of best fit. So to do that, I'm going to use StatDisk, and I'm going to go to Analysis, and then I'm going to go to Correlation and Regression, and make sure that my X and Y values are in column 1 and column 2, or whichever columns I pick. It'll look like this. So I have the mother's heights here, the daughter's heights here. I evaluate. So column 1 is my X variable, column 2 is my Y value. What comes out is my sample size. I sampled randomly 8 mothers and daughters. I get a lot of information here about doing the hypothesis test, which I'll get to in another video. But what I want you to look like right now is the regression results. So we have B naught, which is the y-intercept. We were calling this A on the previous slide. And then B1, which is our slope. We were calling that B on the previous slide. Again, it doesn't matter what you call them. Just know that the slope is attached to X and the y-intercept is the number that's by itself. So my y-intercept is 26.3433 and my slope is 0.6022. So what that means is when I draw my line, I need it to go through the y-axis at a height of 26. And for every 1 unit I move in X, I need my Y to increase by 0.6 units. So this is that interpretation of slope. For every 1 unit change in X, my Y will change by 0.6. So in this example, a 1 unit change in X means that for every 1 inch of a mother's height, we expect the daughter's height to change by 0.6 inches. So let's draw that line on our graph. So in order to draw the line, let's go ahead and write down the regression equation. Again, we know the slope here is this 26.3 number, and the y-intercept is this 0.602 number. And we can go ahead and try using our traditional methods of graphing lines where we start with the y-intercept. But if you look closely at the way that I've scaled this graph, I actually don't meet down here on the x-axis with 0. The minimum x and y values here are 55. So this is really kind of a zoomed in picture of what this scatter plot looks like. So I don't have the physical space on here to graph the y-intercept because the x-axis starts at 55. So in order to do this by hand, we could use the point of averages because we know the point of averages always goes through the regression line. And so if I calculate the average of the x's and the average of the y's, my x bar value here is exactly 64, and my y bar value is just a little bit bigger than 64, almost 65. I could go ahead and plot that point. So here's my x bar, y bar value, and I know the line goes through that. But in order to get the correct slope of the line, I could either count, rise 26 units and run 1 unit, 26.3 and run 1, or I could just find another point that lives on the line. So to find another point that lives on the line, I'm going to pick an x value. So suppose if x, let's say, equals 55, then y will equal, let's find out. So into the equation, we'll have the y-intercept of 26.33 plus the slope of 0.602 multiplied by that given x value of 55. The output here gives us 59.45 if we round to 4 decimals. So according to this regression equation, we can predict that if someone's height is 55 inches, their daughter's height should be 59.45 inches. And so that is another point that's going to live on this regression line. So I'll go ahead and plot it. So x is 55, y is 59.5, so that's about right there. So now I can go ahead and connect this point with this point of averages to draw my regression line. So we can see that that regression line is getting as close as it possibly can to all the green dots in the points in the scatter plot. Remember, it's trying to minimize these residual values, how far away each of these dots are from the line. We're trying to minimize it. But it doesn't actually go through any of the points, and that's okay. What we did over here when we picked this x value and when we picked and found this y value using the equation was almost like a prediction. We said if someone's height was 55 inches, we would expect that their daughter's height would be 59 inches. That's one reason why we could call x the independent variable and y the dependent variable, because if x is this, then y depends on whatever you plugged in for x. Another way of thinking about it is like a call and response. So, this is what we call x out to be, and the response of y is 59.45. So we could extend this, to any other value we were interested in. So we could say if x was 70 inches, then how tall would the daughter be? What would y be? And so all we have to do is plug that x value into the equation and see what comes out. So if a mother is 70 inches tall, then we expect her daughter to be 68.49 inches tall. And we would see that point is here on the line. The equation works the other way too. So if we pick a y value, we can plug that in to find the corresponding x value. Let's give that a try. So if we choose the daughter's height to be 67 inches, and we plug that into our equation, what we are doing then is solving this equation for x. So that solving process first involves subtracting 26.33 from both sides of the equation, which will give us 40.67 on the left-hand side of the equation, and then we still have the 0.602x on the right side. Now we want to divide by that 0.602 to get x all by itself. And we see that x is 67.56. So again, this would be a point on the regression equation. If we go to 67.56, it's about right here. And so up on the line, we see that that output, that y value, is that 67. Well, we're a little off, but it's pretty close. Is that 67 that we had put in for the y. So the ordered pair here is that x is 67.56 and y is 67. Let's bring our StatDisk screen back one more time here. Remember, this did all the work for us. We didn't have to calculate the regression equation by hand because it was all right here, the y-intercept and the slope. But let's return up to these values up here. As mentioned before, those are going to be a part of our hypothesis tests, which I'll do in the next video. But I do want to mention this is the correlation coefficient R that would be used to calculate the slope of the line. And so StatDisk does give you this correlation coefficient R. For this data, the correlation coefficient is 0.82. And our correlation coefficient only will take on a value between -1 and 1. And so 0.82 is pretty close to 1. And what that means is that we have a pretty strong positive linear correlation in the data set here. These scatter plot values are doing a pretty good job of approximating a straight line here. And so the closer this number is to 1, the stronger the correlation between x and y are. Or closer to -1, it's also strong. It would just be a downhill correlation instead of an uphill correlation. In the next video, we'll go ahead and write down a definition for R and talk about what's a strong R value and what a weak R value is.